This is Dr. Arlo Kane, and this is a second mini makeup lecture for Math 20610 Linear Algebra at the University of Notre Dame. The topic is orthogonal sets. So let's start with a definition. A collection of vectors v1 through vk in Rn is called an orthogonal set if vi.vj is 0 for all I different from j. A better way to read this is to say that every pair of distinct vectors in this collection is orthogonal. It doesn't make sense to say that a given vector is orthogonal to itself, so we have to distinguish v1, we're testing this for v1 dot v2 is orthogonal, and so on. So a pair of distinct vectors is orthogonal. As an example, the standard basis of Rn, which consists of the standard unit vectors, this is an orthogonal set. If you pick any two of the vectors in the set, say e1 and e2, then when you form the dot product, of course you're multiplying corresponding entries and adding up the results. Well, you'll have 1, 0 gives a 0, and 0, 1 gives a 0, and all the other products are 0, so the total is 0. And in general, if you pick any distinct pair, the ones are going to be in different places in the column, and so the dot products will work out to be 0. Of course, this isn't the only example of an orthogonal set. Here's an example of an orthogonal set in R3. The vectors 1, 1, 1, 1, negative 2, 1, and negative 3, 0, 3 form an orthogonal set. I've drawn them here to illustrate the orthogonality. It's a little bit difficult to see because, of course, this is a projection of a three-dimensional situation into the 2 dimensions of the video screen, but you can see roughly that this vector is pointing 1 unit in the x direction, 1 unit in the y direction, and up 1 unit in the z direction, so it's coming out toward you, whereas this vector in the back is 1 unit in the x direction, but minus 2 units in the y direction, pointing away, and then 1 unit up. And then finally, negative 3 units in the x direction, 0 units in the y direction, 3 units vertically. And as is suggested by the image, these two vectors meet at a right angle, these two vectors meet at a right angle, and if we were to turn this image around, you would see that these two vectors meet at a right angle as well. So the first theorem that's important for us to study is that if you have an orthogonal set of vectors, all of which are not the 0 vector, then that set is linearly independent. So this gives you a kind of quick way to generate a linearly independent set if you can find a family of orthogonal vectors. Let's go ahead and see the proof of this theorem. If we want to test whether or not this set of vectors is linearly independent, we need to see if it's possible to write the 0 vector as a linear combination of the v1s through vk's. If the only way to do this is with the trivial linear combination, namely the only way to do it is to have all of the c's equal to 0, then the set is linearly independent. If it was not the case, if we could find some non-zero collections, some of the c's were non-zero to make this relationship work, then it would be possible to solve for one of the vectors in terms of the others, making the set, that vector dependent on the others and the set dependent as a whole. All right, so we're going to suppose that it is possible to do this, and we want to conclude that all of the c's have to be 0. If we fix one of the indices I, it could be, say, I is 3, then we can take the dot product of v3 with the 0 vector, and we'll end up with 0. But 0, we're assuming, is written as a linear combination of v1 through vk, so we can substitute for it in this expression. But now we can use the properties of the dot product to distribute vi dot across the vector addition and pull the constants out of the dot products using the homogeneous property and linearity, and we'll end up with the following expression. On the left hand, we'll have 0, and after distributing and pulling out the constants, we'll end up with this combination of dot products. And now here's where orthogonality comes in. So remember that the dot product of vi with vj is 0 when I and j are different. So if I was 2, v2.v1 would be 0, this term would go away, and v2.vk would be 0, assuming k was different from 2. But somewhere along in the list, you'll end up with a match between the I index and the index of the vector you're dotting with, and in that case, you'll get something non-zero. So that's the case when you have vi dot with vi, and all the other inner products worked out to be 0. But then if the index on the vector is matching the index of the vector you're dotting with, I, then that means that the constant that was going along with it has the same index. So you end up with ci out in front. Ci times vi dot vi has to be 0. But now we observe that if we're assuming that every vector in the set is non-zero, then its dot product with itself is non-zero. And then from this equation, you have something you don't know times something non-zero has to equal 0. The only way that can happen is if the thing you don't know, ci, is equal to 0. And we can argue this for each one of the i's. So indeed, all of the scalars have to be 0, which means that the set is linearly independent. Okay, so it's easy to make a linearly independent set from orthogonal vectors, as long as all the vectors in there are non-zero. If you want to form a basis for your space or a subspace of your space, remember that you need two things to happen. You need both the set to be linearly independent, so that there's no redundancy in ways of building new vectors from old vectors by linear combination. But you also need the set to be a spanning set, so that there's enough building blocks to be able to build everything in your space through linear combinations. So an orthogonal basis for a subspace of Rn is an orthogonal set, which is also a spanning set for W. So we shorten that to say an orthogonal basis for a subspace W is an orthogonal spanning set for W. Here is the example we studied before of 3 vectors in R3 that formed an orthogonal set. If we think of the subspace W as the whole space Rn, or here R3 rather, then this is an orthogonal basis for R3 because there are 3 vectors in the set. The dimension of R3 is 3, and so it forms this, and the set is linearly independent because it's orthogonal, so it's a spanning set as well. And so every vector in R3 can be built as a linear combination of these 3, just the same way that every vector in R3 can be built as a linear combination of the standard unit basis vectors, just with different coefficients. Okay, so if we have a given basis and we want to calculate the coordinates of vectors in terms of that basis, we had a procedure for doing this. There's the B coordinates procedure where you can extract the coordinates, and this actually gives you an isomorphism from Rn to Rn. But when you actually go through the mechanics of calculating for a given vector what its coordinates are in terms of the basis, you usually had to do something that turned out to be kind of hard, which was to invert the matrix you form using the vectors in the basis B as columns of the matrix. And if the n that you're working, Rn you're working in is high dimensional, and the basis is then large, this can be a challenging problem. Challenging in the sense that it takes a while to compute. So one of the main benefits of orthogonal bases is that it becomes much easier to calculate the B coordinates when the basis is an orthogonal basis. So the theorem that we're going to prove is that if B is a set V1 through Vk of vectors and it forms an orthogonal basis for a given subspace W of Rn, then for any vector in that subspace, we know that it has coordinates in terms of that basis. But in fact, you can compute those coordinates using simple formulas involving just the dot product, where the ith coordinate of y is simply the dot product of y with the ith basis vector of v divided by the ith basis vector of v dotted with itself. And you can do this for I equals 1 to n. To prove this, let's just write down again what the claim is we're trying to show. We're trying to show that the ith b-coordinate of y is given by this formula. So how can we prove that? Well, y is in the subspace by assumption, and you can expand it uniquely as a linear combination of the vectors in the basis b, and the coefficients of that linear combination by definition are the b-coordinates of y. So what we want to do is figure out how we can solve for C1 through CK and end up with these formulas. And we can do so by taking dot products and using orthogonality. If we fix one of the indices I and take the dot product of this expression on both sides with VI, then on the left we'll have VI dot with Y, and on the right we'll have VI dot with the linear combination C1 V1 plus up to CK VK. And again, just as we did before, we can then distribute the dot product through, pull the scalars out using the homogeneous property, and then we'll have a bunch of dot products, Vi dot V1 up to Vi dot Vk, only one of which will survive by orthogonality, namely the one where the vector we're dotting with in that string ends up being exactly the same as the one we were dotting with on the outside. So we end up with this formula that Vi dot Y is equal to Ci times Vi dot Vi, and because the V's are elements of a basis, they're definitely not the zero vector, so that dot product of Vi with itself is non-zero, and we can divide both sides by it to solve for the unknown, the coefficient Ci. So the benefits of orthogonal bases, again, is that they are easy to calculate with. If you wanted to determine what the coefficients were, or what the coordinates were of the vector 1, 2, 3 with respect to the standard basis in R3, that's pretty easy. You just read off the numbers 1, 2, 3. But if you wanted to determine the coefficients or the coordinates of the vector 1, 2, 3 with respect to this orthogonal basis for R3, our original methods would be rather involved. You would have to suppose it's a linear combination of these basis vectors, turn that into a system of linear equations, and then solve that system of linear equations, either by inverting the matrix B whose columns arise or by doing some other method of solving a linear system, and it would be rather involved. But because B is orthogonal, it's much faster actually to perform that calculation. So let's just note, for example, that for these three vectors, the dot product of the vectors with themselves, which remember is the same thing as the norm squared, are pretty easy to calculate. So the dot product of 1, 1, 1 with itself is going to be 1 times 1 plus 1 times 1 plus 1 times 1, just the sum of the squares of those three numbers, which of course is 3. The norm squared of this vector is the sum of the squares of its components, which is 1 plus 4 plus 1 is 6. And then the norm squared of this is the sum of the squares of its components, which is 9 plus 0 plus 9 makes 18. So if we go back for a moment to the theorem, the coordinates that we're searching for are given by these simple formulas involving dot products. And we just worked out what all the denominators are. So the only thing left to do is to work out what the dot product is with our given vector, 1, 2, 3, and each of the basis vectors, and put those in the numerators, and then we'll have the decomposition we were after. So here's the vector 1, 2, 3. Here are the basis vectors of our orthogonal basis, 1, 1, 1, 1, negative 2, 1, negative 3, 0, 3. The denominators of these fractions, each of these fractions is a coefficient of a coordinate of 1, 2, 3 with respect to this basis. The denominators of these fractions are precisely the dot products of the basis vectors with themselves. So v1 dot v1 was 3, v2 dot v2 was 6, v3 dot v3 was 18. And in the numerators should be the dot products of our y, 1, 2, 3, with each of those basis vectors. So let's just check. If we do 1, 2, 3 dot 1, 1, 1, we end up with 1, plus 2 plus 3 is, of course, 6. If we do the dot product of 1, 2, 3 with 1, negative 2, 1, we'll end up with 1 minus 4 is negative 3 plus positive 3 is 0. And then finally, 1, 2, 3 dot with negative 3, 0, 3 gives us negative 3 plus 0 plus plus 9 gives us positive 6. So we were able to figure out what the coordinates were of 1, 2, 3 with respect to the spaces, namely 6/3 or 2, 0, and 1/3. And we did that without having to invert the matrix obtained by sticking these columns in as columns of a matrix that we did in other coordinate calculations.